chapter 12 and 5, the y to delta the second. And so y connection configuration is quite simple. If we have some element, it could be voltage source, current source, or impedance, whatever it is. Then maybe this will be connected in this way, in this manner. Define this terminal is, for example, A and B and C. Then we define their point is N. And here we can define some variables, voltage and current. Because we have three elements in this circuit, we need to define the three voltage and three current. So we define here. I will define this voltage is V A N. I want to define this is the V B N, and I want to define this voltage in this manner as V C N. And also, I can define the current in the going to the current. No, I'm sorry. Define the current is in this manner is IA. This current is IB, and this current is IC. So in the Y configuration, the voltage and current is very simple. It's very easy to analyze this circuit. But in the point of the delta connections, it's quite different. Delta connection has some three elements in this manner. It could be voltage source, it could be current source, it could be impedance, whatever it is. And then, I move this one here. Then we have also the three terminals here. So we define this is A, and define this is a B, and you can define this is a C. So we rewrite here is this point is the same thing as A, this is the same as B, this is the same point of C. So here we need to define the three voltage and current because there are three elements. So I want to decide name of that is VAB, and I want to define the name of this is VBC, and I want to define this is VCA. Because there are three elements, you can define the three current here. So the current going to here, I define this IAB, and I define the current position is IBC, and also current here is ICA. But our concern is actually not current of the element, because this system is connected with other in here another circuit. So we need to focusing on the current, not only the current of IAA, but also the current going through this IA and IB and IC. So in the Y configuration, there are three voltages and three current. But in the delta configuration, there are three voltages and there are six current. So we call this current is not same with this current is not same with this current. But as we know, if this figure, this configuration and this configuration is the same things, then if two is the same thing, then this IA is same with this IA, this IB is same with this IB, and this IC is same with this IC. When these two circuits is equivalent. So because delta has three more the current we need to figure out the characteristic of this additional current in this current and this current and this current. So now I want to analyze this Y configuration in more detail, Okay, we do that here. So eliminate, okay, we make a simple equation. This is A. Okay, like that. So we need to think about this node A. So you apply KCL in every node, each node, A, B, C respectively. When you apply A, and then what happened? Because this is KCL, there are three current. ICA is going into this, IA is going out from this, IA, the current, is phase current. We call this is line current. Therefore, IA plus IA and plus ICA minus IAB is 0. Our B and C. In the case of B, in plus IB plus IAB and minus IBC is 0. In C, plus IC plus IPC minus ICA is 0. Then if we know if voltage, the line to line voltage, VAB, VBC and VCA, this is line to line voltage. Line to line voltage are known. Then we can calculate IAB. What is IAB? IAB is current going through here, is VAB. So we define the impedance as GAB. This is GCA. This is GBC. Then IA is GAB over VAB. And IBC is VBC divided by GBC. ICA is VCA divided by GCA. And here, if we have some great assumption that if the load is balanced, that means GAB and GB, BC and GCA is the same. Then because VAB, VBC, VCA is balanced and voltage is balanced, that means VAB is V theta, VBC is V theta minus 120 degree, and VCA is V theta plus 120 degree. Then current IAB, IBC ICA is balanced. Therefore, IAB can define is I theta. IBC will be same magnitude in theta minus 120 degree, and ICA will be I theta plus 120 degree. Oh, I have some long this additional theta because current is theta. So I will change this is phi, then this will be phi, this will be phi. Then we can apply this current here. We can apply this current in this here. Then IA is same with IAB minus ICA. Then we apply that here. The result was the same way IB IBC minus IAB, there will be 2 to 3 and I and theta minus 150 degree, and IC is ICA minus IBC. So the magnitude of the line current is root 3 and phase current. So this is a relationship. And phase of IA is phase of IAB minus 30 degree. That means in the phase, line current, we define this current is line current. IABC is we define line current. And we define IAB is phase current. So from that, the line current is magnitude is multiplied by root 3 of phase current. So this is important. And the phase angle is delayed in 30 degree of line current. Line current phase is delayed 30 degree from the phase current. So this can be represented in the phase diagram. So let's say the phase current, we define the current in this manner. If we balance it like that, the phase current, a line current was this. phase current is IAB is, from here, IAB is like that. I theta, IBC is I theta minus 120 degree. ICA is I theta plus 120 degree. Then if let the theta is 0, then the phase diagram of that is simple. So we define this is a IAB, then IBC this is IBC. Because this is minus 120 degree, this is IBC. And ICA, this is ICA, this is plus 120 degree. And from here we get it the line current IA is IAB minus ICA. IAB minus ICA. CA is this, but it's minus. So that is this. This is minus. So we got it. This is IA. This is delayed with minus 30 degree. This is a minus 30 degree here. Then what is B? IB is IBC minus IAB. IBC minus IAB is in this manner here, in these directions. We need to move this a little. Okay. We need to draw this. Okay, right. In this manner. So we have it make in this manner here. BC BC minus AB here. Okay. This is minus Therefore, this is IB. And IC is in the same way we can draw the IC in here. IC. So the magnitude of that, the magnitude of that is √3, and the phase is delayed. The 30 degrees. That's a relationship current between the line current and the phase current in the delta configurations. So we have solved the 3-phase circuit, especially we have assumption that is balanced. The 3-phase. Okay. There are 3 kind of the circuit. The source is Y, load is Y. Source is delta and load is delta. Actually, we have 4 types here. And source is Y and load is delta. And source is delta and load is Y. Every configuration has their own characteristic. Then the Y and Y, delta and delta, Y delta and delta Y has their own characteristic. But in the case of if source and load all balanced, then Y and Y is the most easy to solve the circuit. So when you analyze the circuit, 3-phase circuit, if there are very complicated configurations, then you need to transfer the source and the load to the Y configurations. So it's for example, that means, for example, there are source here is Y configuration source here, like that, and there are delta configuration of load. Then we connect this with in this manner, but there are also some impedance here, line impedance. GL connect this way, and there also the load line impedance, GL is connect in this manner. And there also line impedance. in this manner. Difference GL. Then we need to define some node here. We define this is a small a, this small b, and this is a small c, and this is a large a, this is large b, and this is large c, this is large c, and define some variables. This is VA, VB, and VC. And define the current here. This is I small a large A. This current is I small b large B. And this current is I small c large C. Then we define the current of this direction is IAB. This current is IBC, and this current is ICA. And define the impedance of G delta is balanced, then this is the same things. G delta. So to analyze this configuration, we need to find out what is the IABC. What is IAB? Or we find out this IAA, IBB, ICC in this manner. But it looks quite complicated because the load is delta. It's not easy because we have learned about how to solve the 3-wire systems Y and Y. On 4-wire systems Y and Y. We already discussed about how to solve them. But in the case of delta, it's quite complicated. So in this case, we need to transfer the configuration is Y to I. And to do that here, this is the circuit. Then we need to change only this portion here. We need to change this. We replace this configuration. How can we do that? We can change this with in this manner. This is a GY, and GY. Then if load is balanced, this is Y delta to Y transformation. Then the problem is load is if balanced, then GY is 1/3 G delta. Then we can transfer the circuit like that. Then, because when this is a balanced source, then we can change. We already discussed about how to solve this circuit. Then, fortunately, if source is balanced, the circuit can be more simplified in this manner. VA, and this is GL, and this is a GY, and connect in this manner. This will be small a, this will be large A. Then we can gather the current. This current is IAA simply. So when you have some problem to analysis in Y and delta, delta Y, or whatever it is, then you can transfer the circuit with the transformation. So you need to make a circuit is source is Y and load is Y. Then you can solve the problems very simply. Chapter 7. we need to discuss about the power in the three-phase circuit. If, for example, the three-phase only R load, I mean resistive load, there are no capacitance, no inductors, and the voltage source is imbalanced in the voltage source. This is very simple. This is A, small a, this is small b, and small c. We will define this large A, large B, large A. Then we have a balanced pure register. Let's define this is VA, VB, VC. Then in this case, the instantaneous power in Korean, 순시전력. This can be written here. Yes, I mean the A phase power is consumed by this register, and B phase is this register, and C phase is this register's consumed power. So what is the PA? PA, because this is balanced. Therefore, we need to think about this circuit is in this manner, right? This is RVA because this is balanced. Therefore, the power consumed here is PA is RVA square. Therefore, total power is PA plus PB plus PC. So there will be RVA square plus RVB square plus RVC square. So that the VA is V cosine omega t. VB will be V cosine omega t minus 120 degree, and VC is V cosine omega t plus. That's it. So therefore, we apply that is here. So P is 1 over R VA square, VB square, VC square. So we solve this problem is 3 over 2 R, the magnitude of the voltage, plus cosine 2 omega t plus cosine 2 omega t plus 12 degree plus cosine 2 omega t minus 120 degree. So, and that value, because this is balanced, is 0. So that value is, this is very important. Actually, this is not average power. This is a instantaneous power. I mean, in the case of three phase, there in the single phase, we call this a single phase. The PA will be 1 over R V square cosine square omega t. That was R half plus than here. I mean, this is average values, and there are some fluctuation variables here, like that here. So this is the instantaneous power in the single phase. But in the case of three phase, instantaneous power is constant, even though this source is AC source. In the case of balanced source and balanced load. This is the reason we are using the three-phase the voltage system in the power grid. So if the load is general impedance, we have, having reactance, that means the GA and GB and GC is G and phasing of loading of the theta. Then S is the total, the complex power is A phase, B phase, and C phase. So because this is balanced, then balance it, then SA, same with SB, and same with SC. So SA is VA IA conjugate here, then IA is VAZ. Therefore, this is V theta V and Z theta, then there will be G V theta V minus theta. How about SB? This will be VB IB conjugate. Then IB will be VB divided by G. There will be V theta V minus 120 degree. This is G theta. There will be magnitude is V over Z, and theta V minus theta minus 120 degree. And SC is VC IC conjugate. So IC actually, no, we need to think about this is more things. Oh, no, because these peak values, so we need half. This is peak values. Okay, IC is GVC. There will be the V plus 120 and G theta. So GV theta is theta V minus theta plus 120 degree. Therefore, SA is half VA IA conjugate. Half VA is V theta V. IA conjugate is GV minus theta V plus theta. So it will be eliminate in this manner. So result is half G V square zeta. The same way, half VB I conjugate, there will be half VB V zeta V minus 120, and IB is that values G V minus conjugate minus zeta V plus zeta plus 120 degree. So that result is half GV square zeta. The same way, SC also the same values. Therefore, in balanced circuit, the SA same is SB and SC. Therefore, total S is SA plus SB plus SC. So that will be 3G V square zeta is 3/2. Okay, this is example. I will solve the exam here. Example 12 and 7.2, the 3-phase load. We need to read the problem as well. Balance the load. We have the balanced load and received the 15 kilowatt. This is active power at a power factor of 0.8 lagging, and the line voltage, that means line to line voltage, the same with line to line voltage is 480 volts RMS. Then the problem is the present. And present means this load as a balanced Y connected load. The problem can be represented in there are Y connection is source here, and there are also some Y connected impedance. This is balanced impedance. And this is connected in this manner. Then the line to line voltage is 480 RMS voltage. We define this is a G. This is a VA. We define this is A. This is a large A. This is a small c. This is a small b. This is large B. This is large C. Because this is balanced, that is all is Z. Then we need to find the Z. Then total power is, the P is 15 kilowatt. Then 15,000 watt. The lagging power is 0.8. Then the lagging power, that means inductive power, right? And the power factor is power factor is cosine theta V minus theta I. When you define this is VA, then this current is IA. Then there will be 0.8. Though we know that theta V minus theta I will be arc cosine 0.8. You can calculate that is from the calculator. That is 36.87 degree. And inductive. We got it. And next, we need to know the phase voltages. The line-to-line voltage is 480 RMS. So the phase voltage, the relationship between the phase voltage and line voltages is the line voltage VA magnitude is the smaller compared to the line voltages. So that is RMS. Why? 480 line-to-line voltage is RMS. The phase voltage is also RMS. Then because we got it, the magnitude of the voltages, so then we can say VA, they will be saying with VA will be 277.212 and phase angle is 0. And we can do that. We can do let. Then we know that VB will be same magnitude and minus 120 degree, and VC will be 277.12 120 degree. The unit of that is voltage RMS. Therefore, then we have the complex power is P plus JQ. And that is magnitude of that is cosine theta V minus theta I plus J, the apparent power, and sine theta V minus theta I. So we get it. That is, we already know that is A plus J, because cosine theta V, because we have that values, we applied here, then that is a sine 36 is 0.6. So that value is 0.6. Therefore, P was from here is, so the apparent power S is that values. So that will be that's it. That is 115 plus J there will be one 250. So this is power consumed by 3 phase. So if we consider only one phase, like the SA, there will be the 1/3 S. So there will be 5,000 plus A 3 7 50 unit is VA here. So from that, we can get the current. I mean, SA is VAIA conjugate here. Therefore, IA is SA divided by VA conjugate. Because this is RMS, so we can calculate this equation. If there's a peak values, then SCA will be in the case. Why? In the peak values, peak unit. But this is RMS unit. So we can use these relationships. So here is SA is, then VA is, we define that is here. And conjugate. Then we can calculate the calculator. This is ampere RMS. Why? The voltage is RMS. So we can calculate G. G is VA divided by IA. So there will be 7.212 0 degree and 22.56 in minus 36.9 degree. So the result is 12.28 and 36.9 degree. There is a 9.82 plus J 7.37 ohm. This is a phase, the balance of the impedance of Z. That's your solution. So it's very simple. As in the case of balanced source and balanced load, that we can calculate only one phase and result in the same things in the other three phases.